Is Raphael officially, is he here, Raphael? Yeah? No? Well, not all the organizers are in the room, but thanks to them anyway. And I've been asked to do two separate things in this talk. Number one, talk about some of my own research and that of my collaborators in the spirit of the talks that have been given in this workshop. And number two, to convey some of the ideas of the other workers in the other speakers in the workshop to the broader community here at CERN who comes for the theory seminars, theory colloquia. So my strategy for fulfilling these two competing demands is that I will do a bad job at both of them. I'm going to have to skim over some things, especially for other people's work. I'm going to try to give you, so don't pretend that I'm giving you a pedagogically useful or rigorous discussion, but I'm at least giving the flavor of the kinds of things that we've been discussing here at the workshop. So basically, quantum gravity, this has been something that we've been talking about for a long time now. I guess at least 60 years of serious work on quantum gravity have been done. And there's still the feeling that we don't know the right answer, full stop, to quantum gravity. It's something that we haven't, succeeded in agreeing on what the correct theory is. But we do think that there's certain basic guidelines that we can follow when we're thinking about quantum gravity. So roughly speaking, this workshop has been in the spirit of following the basic guidelines and seeing where you can go, rather than trying to guess or to posit the once and for all correct theory of quantum gravity. So it's a slight exaggeration, but there's not been a lot of talk at the workshop on things like specific models like string theory or loop quantum gravity, ADS-CFT. This is an exaggeration. There's been some talk. Netta Engelhardt just gave a nice talk that used ADS-CFT ideas, but it's been more about trying to ask what kinds of theories can fit the general requirements that we think are going to be true once we do get quantum gravity figured out. What we know is we know what it means to have a quantum theory of something, right? We know that there's a Hilbert space, there's a Hamiltonian, there's an algebra of observables. We know what that would mean, and we're looking for the specific ones that would be relevant to quantum gravity. We know that there's a classical limit that is classical gravity, and there's also matter fields that are described by quantum field theory. So these are things that are, not easy to get out of an arbitrary Hamiltonian, Hilbert space, etc. So that's actually quite a bit of guidance. And the one wonderful thought experiment we have is, of course, the fact that black holes evaporate. Maybe they conserve information along the way, maybe not, but this is going to be something that we'd like to figure out on the basis of our ultimate theory of quantum gravity. So since it might be a heterogeneous audience, I'm going to very quickly remind you of what's in the back of our minds that we get out of this black hole business. I think of this as Stephen Hawking's greatest legacy. The coin that Stephen Hawking gets in England has, the formula for the temperature of a black hole. But more than the result that black holes evaporate, the puzzles that black hole evaporation has left us with are just as important. This is what so many people are thinking about in the field these days. So for those of you who are not experts in Penrose diagrams, this is how people these days think about a classical black hole. That is to say, there's some matter that came in, time goes up, space-time diagram, so time goes up, distance goes right. This is spherical coordinates, so think of this as the center of the universe. And some matter that I didn't draw here would come in, collapse, there's a singularity, and there's a horizon at 45 degrees. The wonderful thing about Penrose diagrams is that light cones are at 45 degrees. So this is infinity out here. And how this changes once Hawking comes along and says that black holes evaporate is something like this. I actually think this diagram is a fake in very important ways, but we're not going to get into that. The point is that evaporation means that there are particles that escape from near the event horizon. They carry off energy, so the black hole shrinks and goes away. And at the end of the day, you're back here in empty space with some radiation going out to infinity. And the formulas that Hawking gave to us say the temperature is inversely proportional to the mass. And there's also an entropy, the Bekenstein-Hawking entropy, which is proportional to the area of the event horizon in Planck units, and the area of the event horizon is proportional to the mass squared, if you want to know. There you go. Black hole evaporation, very quickly done. What do we get from that? We get quite a bit, actually, both good things that are helpful and puzzles that we need to solve. One of the good things that is helpful, that helped inspire this whole thing, is the idea of the generalized second law of thermodynamics. The second law of thermodynamics says that in a closed system, the entropy will either remain constant or go up. There is also in classical general relativity an area law, which says that the total sum of the areas of all the black holes you have lying around only ever goes up. If you take two black holes and squeeze them together, you make one black hole with more than the area of the sum of the original ones. So this was one of the inspirations for black hole thermodynamics, was that these two laws kind of sounded similar, and Bekenstein maybe said that they are in fact identical, and we have combined them now into the generalized second law, which says that the sum of the area of all the event horizons plus the entropy of matter increases over time. So there should be a dt here. I should have put that there. But this kind of thing, this combination of area of event horizons and entropy, is the thing that goes up in closed systems, and that's kind of provocative and interesting, and that's the kind of thing that raises questions that we're talking about in this workshop. So one of those questions would be, what are the degrees of freedom underlying that area equals entropy formula for black holes? If you have the entropy of matter, then our predecessors like Boltzmann and Gibbs gave us formulas for what that means when you have the entropy. It's not just a phenomenological thing. In the quantum context, von Neumann gave a formula for the entropy of a mixed state in quantum mechanics. And in any one of those cases where we have a formula relating the microphysical state to the entropy, there's a space of states and there's some ignorance. We don't know something about the system just on the basis of its macroscopic properties, and the entropy is telling us how ignorant we are about the microstate. So this is one of the reasons why people were reluctant in the early 70s to think that black holes had entropy, because there's nothing we don't know about a black hole. There's very simple things. If you know the mass, the charge, and the spin, and where it is, you know everything there is to know about the black hole. This formula seems to be implying there's a huge number of microscopic states underlying every macroscopic black hole. So what are those? There's some clues from string theory and elsewhere, but it's an ongoing thing in the general case. If you believe this picture, then there's a remarkable consequence that information is lost. If you take a book with information in it, such as my general relativity textbook, which has information, much of it accurate, and you throw it into the black hole, it's going to hit the singularity, and that information is not going to get out to infinity, so that information is now lost. That is the straightforward implication of this picture. You might think, well, maybe the information can be duplicated into the outgoing Hawking radiation, but quantum mechanics says it can't because there is a no cloning theorem for quantum information in quantum mechanics. So still, many stubborn physicists, myself included, think that the information does get out somehow. So that's the black hole information loss puzzle. How can the information get out? At the very least, the most naive interpretation of this picture can't be right, so what is right? Also, these days we have more modern ideas about what happens at the horizon and in the interior, fuzzballs and firewalls and things like that, which I won't have too much to say about, but I'll mention them along the way. Okay, so those are in the back of our mind, and there's sort of two routes to progress that we've been pursuing in this workshop. So, I mean, there's a third route, which is guess the right theory classically and then quantize it. That's what a string theorist would be trying to do. But we, like I said, are not mostly doing that. One route that we can take is to be semi-classical, to sort of keep our feet grounded in things that we think we understand pretty well. Classical space-times coupled to quantum mechanical matter, quantum mechanical fields, and to learn something. I mean, that's where that generalized second law fits in. If you have an area, the word area implies you have a geometry, that implies you have a space-time, that implies that you're classical in some sense, right? Quantum mechanics uses words like wave functions and entanglement. Classical general relativity uses words like space-time and metric and areas. So you consider quantum fields on a classical background space-time, not necessarily one that obeys Einstein's equation. There could be corrections and there could be perturbations. The graviton can be part of your quantized field, etc. And you can use that formalism to think about black hole information loss and deriving other theorems. The other way to go, which is much less grounded and harder, and therefore no one can say you're wrong. Remarkably, people say you're wrong all the time when you try to do this, but they shouldn't, is to be fully quantum mechanical. What do I mean by that? A lot of people who do quantum mechanics, we're human beings, right? So even when we do quantum mechanics, we tend to start with a classical theory and quantize it. That's what you're taught to do with the simple harmonic oscillator or the hydrogen atom or whatever. Presumably nature doesn't do that. Nature doesn't start with a classical theory and quantize it. Why would nature do that? Nature is quantum mechanical from the start. Classical mechanics should be reached as a limit of quantum mechanics. So if you claim that what you're really doing is quantum mechanics from the start, what you have is some quantum state, which is either a vector or maybe a density operator in Hilbert space, and there's an evolution operator and so forth. All the words, like I said, about space-time, fields, and so forth, these are all classical words that might emerge from your quantum description, but they shouldn't be in there to start. They should come out by some procedure. So if you're fully quantum, you have the wave function of the universe, and then you should get space and time, well, at the very least, space. In the Schrödinger equation, time is there, right? It's t. It's d by dt of psi equals I h bar of psi, right? So time is arguably fundamental even in quantum mechanics. Space is certainly not. Of course, there's the Wheeler-DeWitt equation version of the Schrödinger equation, which just says h psi equals 0, and then time is not fundamental. It's emergent. That's a whole other talk that one could give that I'm not going to give today. So, but space could certainly be emergent, and therefore, in this context, the focus is on understanding how you go from Hilbert space to space-space, how you go from quantum mechanical ideas to things like locality, field theory, and so forth. Okay, so now I'm going to give you a lightning review of some of the major ideas that we've already been talking about at this workshop. I give my very sincere apologies to the people whose work I'm about to give a terrible version of. But at least I'm trying. Be patient with me. God's not finished with me yet. All right, so we started the conference with a wonderful talk by Raphael Boussol, who has turned his entire future career into an algorithm. He even has ex-students that work like Stefan Leichenauer at Google, so they can actually just let machine learning write all the physics papers for them from now on. Here's the algorithm. You start with classical general relativity, which is something we know very well, and then you untake the classical limit. You may be suspicious that this is a procedure that ever works, but we know enough, we think, about semi-classical quantum gravity to do this. At least we know what the result should be with some confidence. Black hole evaporation is an example of the kind of thing you calculate. Perturbations of density from inflation are another thing that you calculate using semi-classical quantum gravity. So we think we actually believe, despite the mathematical terribleness of this idea of untaking a limit, we think that you can start from classical general relativity and turn it into some rules of semi-classical quantum gravity. And then you can take the no gravity limit. You could turn off gravity and get flat space-time and get a result in quantum field theory. So the idea behind this algorithm is that you can start with a feature of classical general relativity, which is a very well-defined theory, and derive new results in quantum field theory, which is a whole other theory. Right? And the bridge between them is this idea of semi-classical quantum gravity. So let me give you the most easy to understand but also most trivial example. You start with the area theorem for black holes. The area theorem I already told you, some of the areas of the event horizons goes up over time. You might worry, by the way, about the time reversibility of that statement, but you can fix it. Don't worry. It's not violating the fundamental reversibility of the laws of physics. The translation of the area theorem in classical GR to a theorem in semi-classical quantum gravity is exactly the generalized second law of thermodynamics, which I already told you about. The sum of the area of the event horizons plus the entropy of matter increases over time. And then you take G equals 0, or at least you get rid of this. I'm not quite sure about the mathematical way to do that, because it looks bad. But basically, you take the flat space limit. This is why Raphael's a highly trained compensated professional. You take the limit and you derive this wonderful law of physics called the second law of thermodynamics. Now, sadly, you've been scooped because people already derived the second law of thermodynamics before you got there, but this is an existence proof that this kind of procedure can work, and you then go and actually get much more interesting and novel results by the same thing. I'll talk a little bit later about something called the quantum null energy condition, which is a brand new result in quantum field theory that was derived by a procedure like this. So there's actually some promise for getting new results. So if anyone has, their favorite theorem in general relativity lying around, you could potentially derive new results in non-gravitational physics by this method. Another set of talks, discussion that was given, that I have even less substantive to say about, was about soft modes and soft gravitational hair. So there's an aspect of this that I think I do understand, I think is really neat, And there's an aspect of this that is relevant to this conference, and these aspects are more or less non-overlapping, so bear with me. Here at CERN, we know about scattering particles using Feynman diagrams and so forth, right? So an electron and positron come in, my Feynman diagram goes from the left to the right, they annihilate into a virtual photon, and then they reappear as an E plus E minus pair and go off their own way. And we can calculate this, we've done this, the whole bit. But if you paid close attention, depending on the amount of attention you paid when you took your field theory class, you know that even in this diagram that has no loops in it, there are still divergences. There are infrared divergences because a more accurate version of this diagram would look like this. There's a bunch of photons that are very, very soft that can come out of this diagram. And of course, there are loop diagrams with soft virtual photons inside as well. And there are procedures for dealing with this, but there's an interesting conceptual set of questions. I like to think of this personally as being a reminder that quantum field theory is not quantum particle theory. It's a theory of fields, not of particles. These soft modes are really things going on in the quantum fields that don't rise to the level of being in a first excited state that counts as a real particle. But nevertheless, in the field, especially asymptotically, there can be difference because of these soft modes. So one thing you can do is treat this as a quantum mechanics problem, trace out the density matrix over all these soft modes, and find out what the pointer states are. So there's a whole conversation that I'll talk a little about tomorrow in the colloquium, not get a chance to go in today, about decoherence and pointer states and classicality. But the point is that one of the reasons why quantum field theory actually gives us trajectories of particles in our experiments here at CERN, like why, if the world is made of fields, do we see tracks in our experiments? Well, it's because the pointer states, the robust classical states of the quantum field theory Hilbert space, look like particles' localized excitations. And you can find this by tracing out all these soft photons. That's interesting, but it has nothing to do with gravity. The fascinating prospect for gravity is that, of course, if you can do this for photons, you can do this for gravitons also. So whenever you jiggle anything in the world coupled to gravity, aka anything in the world, you can imagine there's soft gravitons being emitted, and that can cause decoherence also. So the different amount of soft gravitons that you emit can give you different orthogonal states of the wave function. In some sense that is yet to be fully worked out, if I understand things correctly, that means that there's information contained in that soft hair that sends out to infinity. And you can be optimistic or pessimistic about what this means. If you're optimistic, you can say, well, maybe this is helping the information get out of the black hole. There's something that is absolutely true that is related to this, which will come up again and again in the talk, which is that gravity has this, even before you get to quantum mechanics, it has this bit of non-locality in it. When you have a gravitational field, it's a long-range force. It extends to infinity. Electromagnetism is also a long-range force, but you can imagine canceling it. You have a positive charge and a negative charge, so there's essentially no field at infinity, or at least it dies off very quickly. Gravity just accumulates if you obey some reasonable energy condition. So there's some information about your state at infinity in a theory of gravity that is sort of more there than it is in other theories. Maybe that has some interesting ramifications for the eventual quantum theory. There's a lot more to say about this, none of which I will say. The next talk that we heard, Gerard de 't Hooft talked about his ongoing program to understand black hole radiation and the information loss problem. And the claim is something like the following. I'm sure you'll correct me if I'm wrong. Here's a famous diagram. You can see it in my GR book. This is the Penrose diagram for a maximally extended Schwarzschild black hole. Okay, so we live over here, time running vertically again. This is spatial infinity. Here's the event horizon in the future. This is an eternal black hole, so there's no matter in this diagram. It's completely time symmetric. There's a white hole in the past. There's a past event horizon, a future event horizon, the interior of the black hole, and there's also a wormhole, or an Einstein-Rosen bridge, that takes you to a whole nother asymptotic region. The claim is the following, that you can forget about ultraviolet effects, and you can forget about even the actual physical evaporation of the black hole. You can study the evolution of the soft modes outside the black hole and take very carefully into consideration how they scatter off of each other And you can, under certain assumptions, derive an S matrix, which gives you unitary evolution from modes in the past to modes in the future, conserving information. The big leap you need to take is that there's some antipodal identification across, I guess, across this horizon right there. But the important thing is that you can span the whole Hilbert space by either the incoming modes or the outgoing soft modes, and the resulting S matrix is unitary. What does this tell you? I mean, so I think it's supposed to be a claim that the supposed puzzle of information loss is not as bad as it might seem. I mean, this is basically a quantum field theory calculation just done very, very carefully. It didn't require string theory or any assumptions about quantum gravity. Maybe the information loss puzzle is not as bad as it seems, and maybe resolving it in this way tells us something about quantum gravity. Is that fair? Did you okay? Whew, I did okay. All right. So that was much of my half-hearted attempt to give a little bit of an overview, a flavor of what people have talked about at the workshop. I'll mention some other things along the way, but I want to get into my favorite area here in my own work in this area, which is the other approach, rather than the semi-classical approach, to try to be quantum first about it. So again, to re-emphasize something I said, we tend to think of wave functions in quantum mechanics as functions of something. Position of particles or field values or spins or something like that. Presumably nature doesn't work that way. Nature, what you're taught, what you're mentioned in your quantum mechanics class is that wave functions are vectors in Hilbert space. This psi of x is a representation of that vector in Hilbert space in terms of square integrable complex functions over some configuration space. But who cares? There's many ways to represent a vector. The important thing is the vector, the actual state vector. This is, I've drawn here a very tiny subset of Hilbert space. This is 3 dimensions. The actual number of dimensions is something like e to the 10 to the 120, so it's more than this. But the geometry is the same. It's all vector spaces, and vector spaces are very boring. Vector spaces, don't have any structure to them except it's a bunch of vectors, right? There's a little bit of structure in the quantum mechanical case because we also have a Hamiltonian that gives you a preferred basis, the energy eigenbasis. But still, there's not a lot to work with. What you're allowed to work with are these quantum words like states and tensor products and entropy and entanglement. What you're supposed to derive are concepts like particles, fields, forces, metrics, geometries, and stuff like that. So the challenge is, if someone just gives you a vector space with a huge number of dimensions and gives you a particular vector in it, maybe they also give you the set of energy eigenstates, and they just hand it to you and they say, what is it? What does this represent? Is this a harmonic oscillator? Is this a series of qubits? Is this a ferromagnet? Is this the standard model of particle physics? Is this the universe? How do you get that? This is not an easy question. I mean, it's an easy question to ask. I don't know why we weren't asking it 60 years ago, but we haven't made a lot of progress on answering it because a lot of people think that they know what the classical variables are because we look around us, we see the fields in space and so forth. But I take some of the lessons of semi-classical quantum gravity to be that we shouldn't be so sanguine about what the correct classical variables are. We should really start with the quantum description and try to derive them. Okay. So there's 3 different angles. I mean, there's many different angles to do this, but I'll mention 3 of them. One I'm going to mention is ADS-CFT. Even though we didn't talk about it that much at this workshop, it is the dominant thing to do. And you can argue about whether it's really quantum first because you do assume you have a conformal field theory on the boundary. But there's been this wonderful program launched by Mark van Ramstonk and Brian Swingle and others. Ryu and Takanyagi, in some sense, should be here too, where you start with features of the quantum state on the boundary of ADS-CFT and derive geometric features of the bulk. So you're starting with things like entanglement, good old quantum mechanical words, on the boundary, and getting out classical geometry ideas inside. So I'm not going to talk about that, but it's what almost everyone does. So we're a plucky band of idiosyncratic people here, I think, at this workshop. But I like it that way. That's good. But still, if you're a young person, you want to get a job, you should do that. Okay? Here are the other approaches that we can think of. One is to take very seriously the most subtle lessons that we learn from local quantum field theory, especially gauge theories, about these intrinsically quantum mechanical ideas like Hilbert space, entanglement, and so forth. the quantum, there's this sort of informal way we have of thinking about the Hilbert space in quantum field theory, and then there's the right way, and they're different. So there's a lot to be learned about that, and you can do this even sort of at the perturbative level in gravity. You don't need to just do QED. And Steve Giddings has been pioneering this and trying to do it for a long time. And me and my collaborators have been doing something very different. Rather than starting with field theory, we start with the idea that the Hilbert space of quantum gravity is locally finite dimensional, which is very different than what you get in field theory, and trying to get field theory out of some kind of limit. So we have to start with entanglement and get things like space and locality and so forth. So Steve would say that we are ignoring incredibly valuable lessons from gauge theory and local quantum field theory, and we would say that Steve is paying far too much attention to the ideas that you get from local quantum field theory and gauge theory. I'll be very honest, I have no idea who's right. That is fair, though, right? What I just said, right? Roughly fair. That's what I've been aspiring for all my life. So
Steve knows who's right.
Steve knows that. I don't know who's right. I'm a Maoist about this. I want to let 1,000 flowers bloom in this particular kind of thing. I'm not saying that we have the best way of doing it. I think the way that we have of doing it is at least worth pursuing and thinking about. So I'm going to do a terrible job of introducing you to what Steve has been doing on this one slide. His interest has been in this, following up on this fact that gravity is a little bit non-local in a very interesting fundamental way, and what that tells us about the Hilbert space structure of quantum gravity, using the lessons from classical continuum GR and quantum field theory. So we tend to think in quantum field theory that if I have a region of space, I can talk about the degrees of freedom inside and the degrees of freedom outside, and the Hilbert space is the tensor product of those things. Even in quantum field theory, that's not really true. That's like, kind of true to some approximation. Maybe it's true in a scalar field theory. Certainly not true in gauge theories, and gravity is closer to a gauge theory than a scalar field theory. So it's better in gauge theories to define subsystems rather than drawing a region of space and finding its Hilbert space, to use commuting subalgebras of operators. And if you hear people in the hallways talk about type 3 von Neumann algebras, you know this is what they're talking about. That is all you will know, but this is what they're talking about. In gravity, it's even harder because, like we said, in QED, you can imagine canceling the far field by arranging your system of charges, whereas in gravity, everything just accumulates. So if you imagine in some region, starting with a quantum state and then adding a particle with some mass, its gravitational field instantly fills the whole universe. It's Coulomb kind of field. So if I did that with two different operators, they would necessarily overlap. It's very, very hard to define what you mean by a gauge invariant operator. So Steve has a suggestion for at least the beginning of a way of doing it, taking advantage of this split structure kind of structure, if I can say that gravity does seem to respect, where you can imagine factors of Hilbert space that correspond to what's going on in a region and a separate thing that is going on out a region and outside that region. You have to separate them by an epsilon neighborhood. And what is going on has a technical definition in terms of there's a set of operators we can define as being out here, defined by the property that they have the same matrix elements in any state that is the same out here but might be different in there. Okay? So you can imagine nesting sets of Hilbert spaces like that, and they're all included in the big Hilbert space. I think it's safe to say there's a long way to go to build this up into the right structure for the Hilbert space of quantum gravity, but it's certainly taking seriously what we're learning from field theory and perturbative gravity. Now, there's another thing that we know. I know is too strong a term here, but there's another hint that we're getting from black hole thermodynamics, which are the various breakdowns of locality that seem to be implied by black hole thermodynamics. Holography, complementarity, information retrieval. There's various senses in which locality is at least being challenged. I don't think it's a proof in any sense, but there's various good arguments that something has to be a little bit non-local. So for those of you who are not experts, here's the cartoon version of complementarity / holography. here's a black hole, the circle, and if you fall into the black hole, the claim goes, no one has done this and reported back yet, but we believe that you fall into the black hole and everything looks normal to you. If you read, again, a textbook in GR, you'd be told that when you go through the event horizon of a black hole, you don't notice anything. There's no signpost, there's nothing that hits you or anything like that. It's just normal. So you think that the degrees of freedom around you are spread locally like they are in quantum field theory. You have a low energy effective field theory description. Whereas, if you're outside the black hole, you don't see inside. In fact, you don't even see anything go inside. If you throw the book into the black hole, what you see from the outside is it sort of slows down as it comes close to the horizon. And in some sense, its information gets spread out. And furthermore, the counting of the number of degrees of freedom that you have inside that black hole from the entropy, remember, it doesn't go as the volume. If you have a maximally entropic state, the entropy tells you something about the dimensionality of the Hilbert space. Namely, the entropy is the log of the dimensionality of the Hilbert space. So if you thought that there were all degrees of freedom spread locally through the volume, they should scale as the volume. But the entropy of the black hole really scales as the area, which suggests that there's another way of thinking about them where the degrees of freedom really are on the horizon. And the complementarity perspective says, well, it's not that they are on the horizon or that they're inside. It's that it depends on how you look at it. That's what complementarity has been all about ever since Bohr, right? It depends on how you look at it. If you're falling into the black hole, complementarity says everything looks local and ordinary to you. But if you're far away, it looks as if the degrees of freedom are living on the horizon or actually a little bit outside the horizon on the stretched horizon. And that gives you the right counting of the number of degrees of freedom. So there's a whole bunch of things to say about this, which I'm not going to say. Let me just mention a few things. One is that to get the information out, this picture might be helpful if you think that black hole evaporation is unitary. In this picture, from the point of view of the external observer, the information never got in. It's easy to get out. It's always there near the horizon. Now, there might need to be some little slightly more elaborate things. I'll again mention Steve's work on writing down actual non-locality operators in the quantum mechanical description. But that's all, there's no consensus on what is actually going on here. The other thing to mention is that this very picture violates everything I just said about starting with quantum mechanical words, not space-time words. These are clearly space-time words about horizons and areas and things like that. You would like to make the idea of complementarity and holography intrinsically Hilbert space based. You would like a formulation of what you mean by black hole complementarity in the language of Hilbert space itself. So my collaborators and I made a very, very tentative first step toward that, but it wouldn't be impossible to imagine because the way that this guy looks at the horizon is very different than the way that that guy does, because there's different sort of low energy modes that you have access to. Here, the modes that you had that are low energy were high energy near the horizon, whereas when you fall in, they were low energy near the horizon, so you're looking at it in truly different ways. Maybe there's some Hilbert space version of that. Okay, I only have one very simple remark to make about firewalls, which I mentioned yesterday, but I'll just say it again. I want to lower expectations here because it is really quite trivial. But here's an argument that you're often given, often these days, about firewalls, if you go to the right or wrong, depending how you qualify them, seminars. Here is a black hole. Here's some interior degrees of freedom. There's some radiation that left early, C, and then there's some modes of Hawking photons that are either inward and outward or just inside or just outside. You can divide up the Hilbert space different ways. What you're told is that near the horizon, things should look like the vacuum state, and we know that there's a property of the vacuum state that nearby degrees of freedom are highly entangled with each other. So A and B should be essentially maximally entangled if it looks like empty space if there is no firewall. In order for the information to get out, C needs to be entangled with the later radiation, which is B. So B and C need to be essentially maximally entangled with each other. But there's a theorem of quantum mechanics that says monogamy of entanglement. B can't be maximally entangled with A and C at the same time, so there's a logical contradiction. That is what you are told. The only trivial point I want to make is that there's no logical contradiction here. I don't have the solution to the firewalls problem, but I want to point out why this is not a logical contradiction. It's not a logical contradiction because the word unitarity implies a feature of the wave function of the universe, right? Of the whole global wave function. If you're a good Everettian, like I am, and you believe that the overall evolution of the wave function is deterministic, then that's a perfectly good thing to say, and that's where unitarity lives. That's where you have Schrodinger's equation governing the whole wave function. But the fact that there is not a firewall is a fact of what observers measure, right? It is a fact about what you see when you enter that event horizon. You enter the event horizon, you look around, there's no firewall. So that's a statement about what happens on branches of the wave function. It's just like, if you observe a spin, you'll observe it up or down, even though in the wave function it's in a superposition, because by observing it, you branch to the wave function. So a similar point, not exactly the same, because not in the context of firewalls, but the basic point was made by Hertog and Hartle, so I stole their figure. The idea being that you start with some pure state in the past at scry minus, you evolve it upward, and if you're honest, when you emit all these photons and so forth, you branch the wave function of the universe. Every time you think that there is a black hole with a semi-classical geometry, you are necessarily talking about a branch of the wave function, not the global wave function, because you're using classical language, and it's only it's only on branches that things look classical. So there's many different branches that you evolve into. So I don't know if I'm going to undo any good I just did, but just to give you a very, very simple toy model, and again, all I'm going to argue is that it is possible for B both to be maximally entangled with A and with C, because those happen in different contexts, okay? So you define these Bell states, psi plus minus and phi plus minus. We're thinking of A, B, and C all as qubits now to make our life easy. And imagine I have the global wave function where B and C are maximally entangled, okay? That's what I need to get the information out. And it's obvious, so A and D I've chosen to be maximally entangled here also. Clearly, in this wave function, B and A are not maximally entangled. So you might worry that there's a firewall there. But depending on the branching structure, that need not be true. So just by trivial math, this state can be decomposed like this. So this one term becomes four terms, and the difference here is that the subscript, so this is AD, so there's a pure state of A and D, another one of B and C. Here it's AB, so now this is a maximally entangled state of A and B, tensored into a maximally entangled state of C and D, and if you're generous about this, you imagine these four terms in the superposition represent different branches of the wave function. So the point is, this global state in which B and C are maximally entangled can be thought of as the sum of four different branches, and on every branch, A and B are maximally entangled. Okay, as a trivial statement about quantum mechanics. Does it mean that there are no firewalls? Not necessarily, certainly not. All it means is that there was no logical contradiction in the statement that B is maximally entangled with A and C at the same time. So, I think that we need to take this difference between the global wave function and the semi-classical branches more seriously when we think about the firewall puzzle. In the paper that I wrote with my friends, we did a lot of counting of states and talking about complementarity, but I still wouldn't claim it's actually a full solution to any problems. Okay. Now let me get on to what I really want to talk about, which is what we've been doing with some collaborators on trying to put together this emergence of space-time out of the wave function, at least in the weak field limit, at least in sort of the simplest thing. We've really done nothing but very baby steps here. But the primary, first starting point of all this is the idea that we can think of the Hilbert space of quantum gravity as being locally finite dimensional. Roughly speaking, and I'll try to be a little bit clearer in a second, roughly speaking that means in a region of space, the number of degrees of freedom, the number of quantum states, the basis that spans the Hilbert space for that region is finite dimensional. Okay? This is very different than everything we've learned in our ordinary quantum mechanics classes. If you use a simple harmonic oscillator, it has an infinite dimensional Hilbert space. Certainly if you do quantum field theory, it has an infinite dimensional Hilbert space. You might think that if I have a region of space and put a UV cutoff, so I have both an IR cutoff, because there's the size of the region, and a UV cutoff, I get a finite dimensional Hilbert space. But that's not quite true, because every mode inside the box is still a simple harmonic oscillator, and it can have infinitely high energy. The claim is that gravity provides such a cutoff. You can't actually excite all the modes inside the box, because they would be so energetic they would make a black hole that would be bigger than the box. So the claim is that in a region, and this goes back to Bekenstein, but other people more recently have elaborated on it, in a region there's literally in quantum mechanics plus gravity only a finite number of things that can happen. You can try to do more things, but they will always grow beyond the region. Okay, that's a special feature of gravity. And if it's right, which is very conjectural, but if it's right, there's a sense in which quantum gravity should be simpler than quantum field theory. Finite dimensional things are generally simpler than infinite dimensional things. So let's just pursue this possibility and see what happens. So we know what the dimensionality of Hilbert space should be. How many things can you fit inside a region? Well, you can fit things inside a region until the energy gets so high you can make a black hole. A black hole is the maximum entropy state that you can fit in a region of fixed size, and we know what its entropy is, and therefore we know roughly what the dimensionality of its Hilbert space is. So the entropy is the area. That means that the dimensionality of Hilbert space is e to that, which is a really big number. The entropy of the black hole at the center of our galaxy is of order 10 to the 90th. So the dimensionality of Hilbert space to describe that is e to the 10 to the 90th, which is very, very big. Okay? The entropy of the black hole at the center of our galaxy is bigger than the entropy of all the photons and neutrinos and other particles in our observable universe. That's an interesting road to go down of trying to make quantum gravity out of locally finite dimensional Hilbert spaces. There's obvious huge challenges to doing so. You could not, at least naively, you could not have exact Lorentz invariance in a theory where Hilbert space is finite dimensional. The math theorem is that there are no representations of non-compact symmetry groups on finite dimensional vector spaces. The physical implications of that are a little bit unclear, but at least it's a challenge for Lorentz invariance, gauge invariance, and things like that. Another challenge is that despite all of my warnings, exhortations, I'm still using very space-timey language here, right? Talking about a region of space. I shouldn't do that in quantum gravity. How can I get away with that? So at least here I have a little bit of a justification. The idea being that whenever I use words about space-time and geometry and regions, I'm talking about a branch of the wave function, okay? So when I say there is a finite dimensional Hilbert space describing what goes on in a region, I mean on some branch. So this figure is probably incomprehensible, but the idea is supposed to be that there is this decomposition of Hilbert space into an ultraviolet or infrared pieces, or I should have said more carefully, like a macroscopic piece in an environment. And when you trace out the environment, you get pointer states that look like semi-classical geometries. And it's only in those semi-classical geometries that you can identify what you mean by a region. And so what I mean by locally finite dimensional is on a branch of the wave function, there will be a region of space that, roughly speaking, modulo things like gauge theory and things like what Steve is worried about, we can identify a subfactor of Hilbert space with that region. So it's not supposed to be a statement about the whole global wave function, only about branches. Furthermore, I said, okay, over here we know what the number of degrees of freedom is in any region. Our whole universe only has a finite number of degrees of freedom, at least our observable universe, right? So you may have heard the universe is accelerating. There's a positive cosmological constant. There is something called the cosmic no-hair theorem. The black hole no-hair theorem says you throw things, you make a black hole, it settles down to the Kerr solution. The cosmic no-hair theorem says in the presence of a positive vacuum energy, you wait long enough and everything asymptotes to de Sitter space. You have galaxies and you have photons and so forth, but they all leave. They all just smooth out, they leave the horizon, and what we'll be left with, and this is our actual world, what we'll be left with is something that looks like de Sitter space. That's the cosmic no-hair theorem. That has always sounded to me kind of like the process of entropy increasing, right? Entropy increases, and then in a box of gas, it will hit a maximum. You will thermalize, reach equilibrium, and you'll stay there forever, roughly speaking, okay? So finally, years later, I was able to prove it, or rather, Aidan Chatwin Davis was able to prove it, and I got my name on the paper. Borrowing this wonderful formalism from Raphael and Netta, which defines something called Q-screen. So a holographic screen is something you can define in classical general relativity. I'm not going to go through the detailed definition, but following that philosophy I gave you earlier, where you take areas and supplement them by adding the entropy of matter, you can promote a holographic screen to a Q-screen. And so this Q-screen is the screen along which you obey the generalized second law. The area plus the entropy increases with time. So what Aidan and I, so this thing goes up, the generalized entropy, on that Q screen. What Aidan and I were able to do in a very limited context where we already had a homogeneous universe but was not necessarily isotropic, we showed the following thing. If you assume that the generalized entropy increases monotonically and hits a maximum and never goes beyond it, then the space-time geometry that you get will be de Sitter space. So we did that without Einstein's equation, right? The Bob Wald's version of the cosmic no-hair theorem starts with Einstein's equation and shows that you evolve to de Sitter space. We showed that just by demanding that entropy increases, you evolve to de Sitter space. So it's really true. It's like a mini tiny version of thermodynamic gravity, right? But it's really true that in a very quantitative sense, de Sitter space is the maximum entropy state that you can be in. And if you're a cosmologist, or you spend time being a cosmologist, the right way to think about the puzzle of the fine-tuning of the early universe, which we usually think about in terms of the flatness problem, the horizon problem, and so forth, the real puzzle for cosmology is why don't we live in de Sitter space? Why is there stuff in the universe at all? De Sitter space is the high entropy, the maximum equilibrium state. That's where we're going, but we were very far from there in the past. Why is that true is a good puzzle for cosmology. But anyway, thinking of de Sitter as the maximum entropy thing, what you find is that we are approaching a situation where we'll be surrounded by a horizon. Rather than being outside the horizon, we're inside the de Sitter horizon. It has an entropy, and by the logic I used before, there's a finite number of degrees of freedom. And you can calculate what it is. The entropy is roughly 10 to the 120. So the dimensionality of Hilbert space of our observable universe is something like e to the 10 to the 120, which is a very large but yet finite number. What does that tell us about quantum gravity? So this is the picture, and there's so many things we don't know about this. I don't want to keep apologizing on every slide for how little we know, but one of the things we don't know is whether or not that's the whole universe. So you can sort of think about strong and weak versions of horizon complementarity. A strong version, this is space, and this is us in the middle, and this is our horizon. The strong version would say that literally the entire theory of everything is what's going on in this patch. Other people, like over here, will think that they're a patch over here, but that's just some coordinate transformation of our patch. In that case, the whole theory of everything only has a finite dimensional Hilbert space. I think, this is a whole other talk once again, I think that if time is fundamental, if you really have Schrodinger's equation, d by dt of psi, etc., that can't be right because you would usually because then there's an eternity theorem. The universe lasts forever. You would usually be in equilibrium, and you would not be as far from equilibrium as we are now. We'd be Boltzmann brains or something like that. You can save that if you think that it's the Wheeler-DeWitt equation, h psi equals 0, and then time is emergent, and then both the number of degrees of freedom in Hilbert space and the entire extent of history of the universe are finite, which is kind of scary, but at least it's compatible with everything we know. The other possibility is that there is an outside world, and it has an infinite dimensional Hilbert space, and I think that's also perfectly allowed. There's no Boltzmann brain problem then. So the way to think about Hilbert space as a whole is a finite dimensional piece we have access to, and an outside piece which we don't know how big it is. But having the access to only a finite dimensional piece is enough to give you a lot of both puzzles and benefits. One of the benefits is I don't need to think about what is the algebra of observables. In an infinite dimensional Hilbert space, there are inequivalent algebras of observables, but in a finite dimensional Hilbert space, the algebra of observables is just all Hermitian operators, all self-adjoint operators. So you're faced with the issue of why do you represent the quantum wave function in one way or another. I'm zooming through all these little I've written a bunch of papers about this, and they're all provocative, and none of them is definitive, so I'll just give you some of the results. Here's one of the things we suggested. This perspective, where our eventual de Sitter horizon patch has a finite number of degrees of freedom, and what we're doing is we're equilibrating to it, right? That picture suggests a way of thinking about cosmology in the real world. When you have a finite number of degrees of freedom, and when you have some version of locality in your dynamics, it is natural to use a quantum circuit or a tensor network to model your dynamics. That is to say, you have a bunch of qubits or some qubits, some tiny little Hilbert spaces, and they go through a bunch of gates which entangle and interact the quantum information, the quantum states in those qubits. And cosmologically, you can imagine that you just build up space-time over a period of billions of years through these quantum gates. And the nice thing is, there's two nice things. One is that this can only go on for so long before you've equilibrated, right? So it can only go on so, we haven't equilibrated yet, so it can only go on so long to the past. In other words, if you take this picture seriously, there was a first entanglement in the history of the universe, right? Before that, nothing was entangled. I should say the other cool thing is that it helps me personally understand this worry I always had about when the universe expands, where do the degrees of freedom come from? Like there's an infinite number of degrees of freedom and it looks like they get created at the Planck scale or something like this. In this picture, that makes perfect sense. They were always there, those degrees of freedom, but they were unentangled. The early universe had like 2 entangled qubits and everything else was just an ancilla qubit which was unentangled, and the expansion of space represents the gradual entanglement of more and more qubits. But running that movie backwards, there was a first entanglement, and we can work out the math. It happened about 70 e-folds before the end of inflation. Semi-classically, we often talk about theories of inflation that lasted for thousands or millions of e-folds. We're arguing that quantum mechanically, that's a fairy tale. There was nothing relevant to our universe that happened earlier than 70 or 75 e-folds before the end of inflation. What the observational consequences of that are, I don't know. Okay, so the last topic I want to do is based on this idea, which Ashmeet Singh and I have called Mad Dog Everettianism. Why do we call it that? So Everett, his version of quantum mechanics, is really just the statement that you have a Hilbert space and a Hamiltonian, Schrodinger's equation, and the wave function evolves unitarily. That's it, right? All of the things you've been told in your quantum theory, quantum mechanics course as a youngster have to do with collapses of the wave function, all that comes out from the dynamics of Schrodinger equation, decoherence, etc. However, as I've hinted at before, usually you also imagine you have some preferred algebra of observables. So you can say, oh, here's X, here's P, or whatever it is. If your Hilbert space is finite dimensional, you don't have that. There's no reason to prefer one set of observables over the other. So here is all you're given to specify the evolution of the universe. The dimensionality of Hilbert space, the spectrum of the Hamiltonian, the set of energy eigenvalues, and the components of the wave function in that preferred basis given you by the Hamiltonian. So you're given a list of 2 lists of D numbers, D real numbers, the energy eigenvalues, D complex numbers. Someone hands you that list and you're supposed to say, oh, this is a 3-dimensional space-time expanding, over the course of billions of years. How do you do that? There have been, of course, this idea that entanglement has something to do with space-time geometry. It's been most vigorously pursued in the context of ADS-CFT, as I've mentioned. I just want to make the tiny little snarky comment, maybe I can get away with this audience, that in terms of quantum gravity, the old joke about the drunk guy looking for his keys under the lamppost, and he couldn't find them, and the guy says, well, are you sure you dropped them here? And he says, no, I dropped them over there, but the light is much better here under the lamppost. So ADS-CFT is the world's brightest lamppost when it comes to quantum gravity. We have equations, we can solve them, full employment, we're happy, okay? But it's not the world. It's not where we live. The actual vacuum energy is positive. So I'm very optimistic that you can learn lots of cool stuff by doing ADS-CFT, but I don't want to lose sight of the fact that eventually we want to go back into the world, right? The world, that's our goal as physicists is to describe the world in which we live, in which lambda is greater than 0. So can we somehow say something about entanglement and geometry in the bulk of space-time without using the benefit of an ADS boundary? Can we do that? So again, we're going to be as naive as possible, and we're right for the moment just going to work in the weak field limit, hoping that someday we'll be able to include all those non-localities and subtleties that I referred to. So, and I'm also going to ignore the subtleties of gravitational dressing and non-local algebras and all that stuff. And maybe that's a huge mistake doing that, but maybe it's still a useful first step. So you imagine that, you might imagine that if you had a field theory, you could take the Hilbert space and divide it up into regions. We have a finite dimensional theory, so it's actually more legitimate to do this than in field theory. And then you could write down the most general Hamiltonian if you did that. And the most general Hamiltonian is a set of operators acting on the individual regions, and then a set of 2-point interactions, 3-point interactions, etc. Our real world evolves according to a Hamiltonian, which is very far away from being random. Okay? The real Hamiltonian of the world has very specific properties. Why? I don't know. That's above my pay grade, but I'm going to make use of the fact that it does. In computer science language, a k-local Hamiltonian is one where this series basically truncates, where you only have k-point interactions, not 10 to the 120 point interactions. And there's a nice little theorem proven by Kotler et al. A couple of years ago that says that most Hamiltonians are not k-local at all. Okay? That's a reflection of the fact that our world is special. The laws of physics are not random. There's some structure there. And when there is a local way of writing the Hamiltonian, so in other words, this problem is not, this problem is, can you find the factorization? There's an infinite number of ways to factorize Hilbert space into smaller pieces. Can you find the right one? If you started with space and had regions and said there was locality, then you have it. But if you start with the spectrum of the Hamiltonian, can you derive how to decompose Hilbert space? And what Kotler et al. Say is yes. When there is a local decomposition of the Hamiltonian, it is essentially unique. There's a little subtlety there that I won't get into, but it's pretty close to being unique. Basically because the number of parameters that specify a k-local Hamiltonian is way smaller than the number of possible Hamiltonians you could write down, the dimensionality of that space. So local Hamiltonians are special, and when you have a local Hamiltonian, you can figure out how to decompose Hilbert space so that it looks local. That's what Kotler et al. Did. What we're going to try to do is to go from this kind of graph structure. Here are different factors of Hilbert space, and they're connected if they interact with each other. Now we're going to put a state, which is going to be something like the vacuum state, on this Hilbert space, and we're going to use that to get not just the topology of the network, but a geometry of it. I have to zip through this fast, but I think you folks are experts in these concepts anyway, so it shouldn't matter. When I have a state in this factorized Hilbert space, I can always take some sub-region of it, and I can calculate its reduced density matrix and its entropy, right? Why I'm doing this is because I want to get the geometry of this emergent space out of the entanglement structure of the state. So the entropy is a way of quantifying the amount of entanglement between this region and everything else. I can go beyond that and talk about the mutual information between any two regions. The mutual information is a way of saying how entangled these are with each other versus just being entangled with the rest of the world, okay? If you're a field theorist, every time I use the mutual information, in the back of your mind, you should just think two-point function. Because the mutual information is sort of always greater than the properly normalized two-point function of any operators. From our point of view, where we don't have a preferred set of operators to lean on, it is more convenient to just use the mutual information rather than the two-point function. But you know what the two-point function does in the vacuum of a quantum field theory. It goes down as you get further away. So the normal statement we would make is the correlator decreases exponentially or as a power law, depending on what field you have, but it decreases with distance. What we're going to do is turn that around. We don't know what distance is, but we know what the mutual information is. So we're going to assert by fiat that what we mean by distance is that if you're highly entangled, the distance is small. If you're not very entangled, the distance is large. Now, obviously, if you have two particles, they can be as entangled as you want and be as far away as you want. So we're talking about modes in the vacuum, which have a very specific entanglement structure. So by doing that, and this was our first attempt. We came up with a better way of doing it using surfaces rather than lines and radon transforms and other stuff I don't have time to get into. But basically, you have put an emergent metric on this graph. And then you can do what is called classical multidimensional scaling to find the best fit smooth geometry for that graph. It's all just math and wild assertions. So now we're gonna steal this wonderful trick from Ted Jacobson. So Ted wrote a couple of papers, 20 years apart, on deriving Einstein's equation from entropy. Okay, and I'm gonna say this in the context of our way of doing things. Ted is doing things in the semi-classical context where you have a space-time, you have some fields on top of it. We're doing it directly in Hilbert space, but it's exactly the same procedure. So you can read his paper to learn more about it. The fundamental leap is this idea, which in our setup is automatic, that if you perturb your state a little bit, the area of a surface changes, and the entropy of that set of degrees of freedom also changes, and they're proportional to each other. Okay? You can either treat that as an assertion, or for us, we're treating it really as the definition of area in some sense. That's the sort of leap that you make, and then Ted shows that you can take that area, make it the area of a little tiny ball, relate it to the spatial curvature, relate it to the 0, 0 component of the Einstein tensor, in an appropriate embedding of that space into spacetime. And then you can take the entropy and relate it, and I'll get to this on the next slide, into something called the modular Hamiltonian, which tells you something in the infrared limit about the energy density. So from delta A is proportional to delta S, you derive G00 is proportional to T00, and then if you're Lorentz invariant in the infrared limit, that's just Einstein's equation. Because the only way to have G00 proportional to T00 in every frame is to have G mu nu proportional to T mu nu. So basically, this is saying that from this ansatz, that area perturbations are proportional to entropy perturbations, Einstein's equations follow. And for us, that top line is actually comes out naturally. So the work is being done in this modular Hamiltonian thing. So if you have, let's see, how long do I have? Should I end up soon?
You're pretty close.
I should wrap up soon. Okay. All right. I'll just talk faster. I know everybody likes that. If you have some state and you take some region so it has a density matrix, you know that if it were thermal, the density matrix would have the form e to the minus h, where h is the Hamiltonian. That's the form of a density matrix, of a thermal density matrix. But even if it's not thermal, there is some operator k such that you can write the density matrix as e to the minus k, namely minus log of the density matrix. And I can always define that, right? So k, called the modular Hamiltonian, is what the Hamiltonian would have to be for that state to look thermal with respect to it. You can't stop me from defining that. And then Rob Myers and some of his friends derived something called the entanglement first law. Again, when you perturb the state a little bit, the perturbation in the entropy is equal to the perturbation of the expectation value of this operator, the modular Hamiltonian. Okay? That's the entanglement first law. And the nice thing is that this thing is called a modular Hamiltonian, and it's sort of, I made it up, or I didn't make it up, it's been made up. But in the right circumstances, it actually is the Hamiltonian, or at least it's really the energy density. So I wanted to just put on the table something that was invented here at this meeting. I promised to give a little bit more notice to the quantum null energy condition that Raphael and Stefan and other people derived under certain circumstances. The expectation value of a null component of the energy momentum tensor is greater than the second derivative of the entropy, properly understood, and properly understanding it takes a lot of effort. But Steve Giddings asked the question, so this is very space-timey, energy momentum tensor, area, things like that. Is there a pure Hilbert space version? So my conjecture is that if there is a pure Hilbert space version, it has to be a close relative of the entanglement first law. Because if you think about the null component of the stress tensor, that's like the 0, 0 component plus the 1, 1 component. And that's greater than the 0, 0 component, plausibly, if the pressure is positive. Doesn't have to be, but it's plausible. And that's just the modular Hamiltonian, and that's the entropy. So you can imagine this TKK greater than or equal to delta S kind of has the same kind of flavor as that. So someone should go prove that, is my homework to you. Bob is proving it in his head. I can see the gears going. All right, good. On the other side, that's the right-hand side. On the left-hand side, you have this, you change the curvature of space a little bit by changing the entanglement structure, because that's how geometry is defined. And you can then therefore relate the spatial curvature to the modular energy, and then in the infrared limit, that modular energy is just the energy density in a conformal field theory, so you've derived Einstein's equation. Ted Jacobson derived Einstein's equation. So what we did to add to Ted's point of view was to replace a background semi-classical space-time with a pure Hilbert space construction. It only works in the weak field limit thus far. What we really did, this is Charles Tao and I, we wrote a paper which said the following thing. We wrote an explicit list of assumptions, right? I think we had like 12, I don't know, some long list of assumptions. Some of them are very, very plausible. Some of them are just aspirational. But we said if every single one of these is true, then you get Einstein's equation for an emergent space-time geometry. So every one of those assumptions deserves a paper justifying whether it's true or not. That's why I say we're just taking baby steps in this direction. All right, so this is the last slide, just to give you the reminder where we were and where we came from. So clearly, just semi-classical gravity is incredibly useful, incredibly educational and provocative. For example, it hints at the possibility of non-locality in black hole evaporation. But we also want to get a full quantum theory. Maybe we get there from Hilbert space directly rather than quantizing some classical variables. And there's, again, hints that that's the right thing to do. You can kind of get Einstein's equation in the right limit under the right assumptions. But there's so much we don't understand. This is a wonderful set of ideas to start playing with if you're young and ambitious and don't mind not being completely sure about what you're doing. All right, thank you very much.
Thanks, Sean, for a very nice talk. And are there questions? We might try to use the mic if I can get it started. There we go.
Hi, yeah, thanks for the nice talk. Coming back to the cosmic no-hair theorem that you talked about, that you proved using the assumption of the validity of the generalized second law.
Right.
So can actually everybody hear me?
Yeah, that's good.
Okay. Sorry. So indeed, there's this version by Wald where he proves it using the Einstein equation. So now you have basically a version where it follows from the Einstein equations and then also from the generalized second law. Do you think there would be a possibility to use or to relate these two versions, or maybe to even to make statements like if the generalized second law holds under certain conditions, then also the Einstein equations must hold, or vice versa? Is there anything like this?
Yeah. So sorry, finish.
No, maybe you can go on. So, I mean, I'm just thinking about whether there would be a way of deriving the Einstein equations from an entropic perspective in an analogy to what Ted has already done. Yeah.
Right. I would love to do that. I thought about doing it. Like that's why I said very quickly, it's kind of like a baby version of entropic gravity. I failed mostly because the GSL is an inequality. Right. It's hard to derive inequality from an inequality. Now there is a famous equality, the Jarzynski equality, from which you can derive the second law of thermodynamics in the conventional form. I don't quite know how to make sense of something Jarzynski equality like in the semi-classical quantum gravity case. So that would be my hope to how to do it, but I have not actually done it.
Okay. And then maybe another brief remark. So, I mean, on this expansion of space that we were just describing using these circuit models, are you familiar with the notion of asymptotic silence in general relativity? So it seems to remind me a bit at a very qualitative level. So in mathematical relativity, it's related to the BKL scenario. So it's really about basically that towards the initial singularity, spatial derivatives don't matter, and so basically, in some sense, nearby points don't talk to each other. So in that sense, it's asymptotic silence. So at a qualitative level, that seems to me to be some vague relation here, maybe.
Maybe. So I love the phrase asymptotic silence, but I need to think about what it means more. Yeah. I mean, certainly there's something, and this is why it's important to do de Sitter space, not just anti-de Sitter space. There's something attractor-like. So we did actually, there's another paper. In this paper, we used this kind of formalism to prove a different version of the cosmic no-hair theorem. We modeled de Sitter space, so this is like it's supposed to be an FRW cosmology. We modeled de Sitter space as a quantum circuit. And so the geometry of the quantum circuit is fixed, but then we imagine putting different states into the quantum circuit. And what you find is that they approach a fixed point in the future. So that's sort of the version of the cosmic no-hair theorem. You reach a unique vacuum state. So I do think all these things are related, and I'm not sure what the best angle to take on them. I'm in favor of all the different ones being taken.
Yeah, sure. No, it seems just like there's some qualitative analogy.
Yeah,
if you
it could very well be.
Entanglement to geometry.
Okay. Other questions or comments? Yes.
So you mentioned this question of time, how it enters the picture. So could you maybe reiterate on maybe this example of how you understand time in the situation where you have emergent geometry, but this is geometry of space-time, or so how do you understand time in more general terms? Yeah, no, good. I think that there's clearly two paths and a fork in the road between them. One path is the fundamental equation is the Schrodinger equation, h psi equals id by dt psi. If that's true, number one, time is fundamental. There it is. It's t. It may be related in a complicated way to coordinate time or proper time on the inversion space-time manifold, but there is some time coordinate. And number two, that time goes forever. In the Schrodinger equation, there's no initial singularity. Time goes from -v to infinity, full stop.
So if that's the world, then the Big Bang presumably was not the beginning of our universe. It was just the phase through which the universe went. I think that's completely plausible, except if the entire Hilbert space is finite dimensional. If the entire Hilbert space is finite dimensional and you last forever, then there's a recurrence theorem, a Boltzmann brane problem, etc. So time is fundamental, Hilbert space is infinite dimensional. If time is not fundamental, if h psi equals 0, which is sort of the suggestion from classical gravity, right, the Wheeler-DeWitt equation, then you can get emergent time. There's a number of different ways to do it. The way I like to think about it goes back to a paper by Page and Wooters in the 80s. So they said I can decompose my Hilbert space into a clock subsystem and a rest of the universe subsystem, and nothing changes. The wave function is static, but I can show that under the right circumstances, if I observe the clock, so I collapse the wave function onto an eigenstate of the clock, then the rest of the universe is in a state that has certain properties such that different clock readings look like different evolutions of the universe. So time is emergent in that sense, in that it is a subspace, a factorized subfactor of Hilbert space that has certain definite properties. In that case, Hilbert space could be infinite dimensional, but then I don't understand why the entropy of the early universe was low or anything like that. So, and there's something called the clock ambiguity that Andy Albrecht has worked on that has not gotten very popular, but it goes back to this question of what is your preferred set of observables? When h psi equals 0, remember I said for our program, for the, what did I call it? Nope. So we had Mad Dog Everettianism, remember? So the data we had to work with was this finite set of numbers, the components of the state and the energy eigenvalues. If h psi equals 0, you don't even have the energy eigenvalues. You just have 0. So there's no preferred basis to express your state in. There's almost nothing to work with. So it's very hard to get time to emerge. The only way I know how to do it is to make the quite bold leap to say that the state of the quantum state of the universe is not pure. The fundamental quantum state of the universe is a density operator. And then you have the modular Hamiltonian, and then you can play modular Hamiltonian tricks.
I see. So this is how you understand time in that picture where you had the entanglement and time written underneath.
So what I've been implicitly assuming is that time is fundamental. I've been deriving the geometry of space and assuming that that can be interpreted as space in synchronous gauge, okay, and build up space-time through the time evolution of that geometry.
Okay, maybe one more question.
So this picture you have with the entanglement of the circuit is not special for gravity in principle. You could also make some kind of exercise, let's say derive kind of gauge theories from something or other properties, let's say, not just for checking, let's say, this whole idea.
I think what is special is this assumption that delta A is proportional to delta S. So in a generic field theory without gravity, I can easily change the entropy without changing the area. So in some sense, the assumption here is that gravity has this special property that whenever I change the entropy of a subsystem, its geometry compensates so that it's proportional to the area. That's very special to gravity.
It looked like, did you have a question also, Gerard, or quick question or comment?
Just a short comment. You start with quantum mechanics as being whatever it is without any changes, but you can think of further trying to find the foundation of quantum mechanics, which from my point of view is it's a vector representation of what could be a deterministic theory. So you could go back to hidden variables that would make enormous constraints, restrictions on the Schrödinger equation. So that could be also part of the program. Go even further back before quantum mechanics.
Yeah, no, I'm all in favor of that. My own, one has to vote, right? So my own vote is for Everettian quantum mechanics, and so everything I did was either explicitly or implicitly within that framework. But I don't want to take that for granted. If you can find if there exists some Bohmian or even dynamical collapse or spontaneous or induced collapse models that would give you different phenomenology, then that would be great. I want to let all the different competitors be explored here.
Okay, well, thank you again for a very nice talk.